the atrial septum forms and functions both prenatally and then postnatally. Now, let's go back and take a look at how this relates to the illustrations that are in the notes. In this first illustration, what we see, here's the atrium. There's septum primum that's growing down. There's the endocardial cushion that was in the atrioventricular canal. So septum primum is growing towards the endocardial cushion. It hasn't reached it yet, so there's this opening called foramen primum, allowing blood to flow from right to left. We go a little bit later. We see that septum primum has come down and it has now fused with the endocardial cushion. Therefore, there is no longer a foramen primum. But before that happened, remember, foramen secundum opened. So we still have a pathway for blood to flow from right to left. We see the beginning of the formation of septum secundum coming down on the right side of septum primum. And then as we follow that, we see it continues to come down. It overlaps the foramen secundum. But because of the pressure gradient and because of the flexibility of septum primum, the pressure gradient pushes septum primum away from septum secundum, creating this pathway through which blood can flow. And that pathway is the foramen ovale. And then, after birth, the reversal of the pressure gradient pushes septum primum up against septum secundum. Those two are pushed together, and therefore blood cannot get from left to right, and we've separated the atria. Now, at the time of birth, as a result of that pressure gradient, what I said was that the two septa get pushed together. I did not say that they fuse together. In most people, they eventually fuse. Over a fairly long period of time, they eventually fuse in most people. But in some people, they don't fuse, or they may fuse partially, or not at all. It doesn't matter whether it fuses or doesn't fuse, as long as the pressure is higher on the left side than it is on the right side. You can have an unfused foramen ovale that will be perfectly competent, will not allow the passage of blood because the pressure gradient keeps it pressed closed. Okay? And that's called propatency of the foramen ovale. And that occurs in a significant minority of people. Okay? But it's functionally irrelevant unless something else happens in that person that will result in an increase in pressure on the right side. So if somebody were to develop a substantial pulmonary hypertension so that the pressure on the right side got high enough so that it was higher than the pressure on the left side, a person who had an unfused foramen ovale would then develop a shunt from right to left through that unfused foramen ovale. Okay, so the only time it matters whether it fuses or didn't fuse is if the pressure on the right side rises to be higher than the pressure on the left, which of course is abnormal. Okay, so let's now talk about what are the things that can go wrong in the formation of the atrial septum that will result in atrial septal defects. Now, atrial septal defects are categorized as two different types of defects, and those types are called primum type atrial septal defect and secundum type atrial septal defect. The abbreviation for atrial septal defect is ASD, and I'll frequently use that. So going back to the story of how the atrial septum forms, remember we said that normally septum primum grows down and fuses with the endocardial cushion. But what if that doesn't happen? What if septum primum and the endocardial cushion don't fuse? That would mean that we would have a persistent foramen primum. Foramen primum would remain open. And because we now have this foramen primum that's not being covered over by anything, we would have a communication postnatally, as well as prenatally, between the right and left atria. Now, prenatally, the shunting through that defect would be from right to left. And that's perfectly okay, because we already have a shunting from right to left through the foramen ovale. So shunting from right to left prenatally is not a problem. But postnatally, what will happen is when the pressure on the left side rises, as it does right after birth, so it's higher than pressure on the right, we will in fact have a shunt. And we will have a left to right shunt. So that's called a primum type ASD, primum type atrial septal defect. It's a failure of closure of the foramen primum, which is a result of a failure of the fusion of septum primum with the endocardial cushion. Results in a left to right postnatal shunt because the pressure on the left side is higher than the pressure on the right side. Now, because the blood on the left side is oxygenated blood and the blood on the right side is deoxygenated blood, that means we're taking oxygenated blood and we're sending it back to the pulmonary circuit. So we're taking oxygenated blood and sending it back to the lungs to get more oxygenated. That does not cause cyanosis. Cyanosis, so we call this kind of a defect an acyanotic defect. A left to right shunt is an acyanotic defect. It does not cause cyanosis. Cyano means blue. So cyanosis means that the baby has a bluish appearance. Its mucous membranes, its lips, its nail beds, and so forth have a bluish cast because of the presence of deoxygenated blood or less than fully oxygenated blood in the systemic circulation. So if we had a shunt that was shunting blood from the right side to the left side, a right to left shunt, deoxygenated blood to the left side, that would be a cyanotic shunt. But a shunt that is taking blood from the left side, which is oxygenated, and sending it to the right side, to the pulmonary circuit, is an acyanotic defect, an acyanotic shunt. So atrial septal defect is an acyanotic defect. Similarly, we're not talking about it yet, but when we talk about the ventricle, if we have a ventricular septal defect, which is actually the most common of all congenital heart defects, 20% of congenital heart defects are ventricular septal defects. An isolated ventricular septal defect also, for the same reason, is an acyanotic defect because the pressure on the left is higher than the pressure on the right. So that's how a primum type ASD occurs. Now, I said that the basic problem is that the septum primum and the endocardial cushion don't fuse. And remember, we said that normally the septum primum grows down to the endocardial cushion, and at the same time the endocardial cushion grows up toward the septum primum. And what we now understand is that that defect is primarily a result of a failure of the endocardial cushion to grow up toward the septum primum. So the primary culprit, so to speak, in primum type ASD is the endocardial cushion. An inadequacy, an insufficiency of endocardial cushion cells so that the endocardial cushion does not grow up. As it turns out, the endocardial cushion is formed primarily from neural crest cells that have migrated to the heart tube. And so, once again, a primum type ASD can be viewed as a neural crest migration defect. And so again, it wouldn't be surprising that you find primum type atrial septal defects in children who have other neural crest migration defects. There are a variety of syndromes in which that's found. The other point to be made is that we see that this endocardial cushion is sitting right between the two atrioventricular canals, and we know that each of those canals has within it a valve, the tricuspid valve on this side, the mitral valve on this side. And as it turns out, not a big surprise, the endocardial cushion is a major contributor to the formation of those valves. And so it shouldn't be a surprise that when you have a primum type ASD, there's a statistical correlation in the coexistence with a primum type ASD of valvular defects. So kids who have primum type ASD have a fairly good chance of also having valvular defects because the same endocardial cushion that had an insufficiency of neural crest cells so that you were left with this defect here, that same deficiency in neural crest cells will result in deficiencies in the tricuspid and/or mitral valve. So there's a statistical correlation between that defect and valvular defects. Okay, so that's one kind of atrial septal defect. The other type of atrial septal defect is called a secundum type defect. And the way that forms goes back to how foramen secundum forms. Remember, we said that foramen secundum forms as a result of programmed cell death that results in a perforation of the septum primum. So this process called apoptosis, which results in a loss of cells so that this hole forms, if that process is excessive, if there's too much apoptosis, this foramen could be too large, and we could end up with something like that, with an excessively large foramen secundum, with the important point being that foramen secundum is now so large that the septum secundum is no longer completely overlapping it. And so we have this region of the foramen secundum that's not covered over by septum secundum, so that when the pressure gradient reverses and the left side pressure becomes higher than the right side pressure, which it happens at birth, and we normally would have septum primum pushing back up against septum secundum, because they're not overlapping, they can't be pressed together, and therefore you're left with this patency. So in essence, this would be this is called a secundum type ASD, and in essence what it is a persistence of the foramen ovale, an inability of the foramen ovale to close, because remember, closure of the foramen ovale required an overlapping of these two septa so that this could get pushed against that. If that doesn't happen, we have a secundum type defect. Now, since that secundum type defect has nothing to do with the endocardial cushion, and therefore nothing to do with neurocrest cells of the endocardial cushion, this is not a neurocrest migration defect. And again, since it has nothing to do with the endocardial cushion, this kind of an ASD, a secundum type ASD, is not correlated with valvular defects. They're two unrelated events. Secundum type ASD is the much more common of the atrial septal defects. It's about 8 times more prevalent than primum type ASD. Now, if you were to look into an atrial septum, of course, as before, this would be a left to right shunt, so it's an acyanotic shunt. If we were to look into the atrial septum, and if we were to see a hole in the atrial septum, somewhere on the atrial septum, not shown here, but if there were to be a hole, a septal defect on the atrial septum, we should be able to surmise which kind of atrial septal defect it is, a primum type or a secundum type defect, based on its location. So we know that since a secundum type defect is in essence a failure of the foramen ovale to close, we would expect to find a secundum type defect in this region of the septum, in the region of the limbus of the fossa ovalis, where there normally is overlap of secundum with primum, septum secundum and septum primum. So the upper part of the fossa ovalis is the region where you'd expect to find secundum type atrial septal defects. And then the region next to the tricuspid valve, which is where the endocardial cushion was, in other words, that region there would be the region where you would expect to find primum type atrial septal defects. And so that, in fact, is the case. So in this region is where primum type ASD occurs, and in this region, that's where secundum type ASD occurs. So if we know the location of the defect, we know the type of the defect, and if we know the type of the defect, we know what the developmental mechanism was that resulted in the defect. Okay.